Alright, hello everyone. Welcome back to our reading of categories in Sheaves. We're picking up where we left off last time. We're talking about exact functors. Last time we introduced the definition of an exact functor, and, well, modulo the easy direction that I conveniently forgot to do but left in the video description, we proved that functors are left or right exact when they commute with projective or injective limits, respectively. And this time, we're going to continue in this train of thought. We're going to prove the, we're going to prove the other common statement about exactness from commutative algebra, namely that a functor with a right adjoint, or if you like, is being a left adjoint, is right exact. And in some sense, then we sort of feel this is clear because we saw right adjoints preserve limits, left adjoints preserve colimits. So this should be very straightforward, but we're going to give it a proof of this that uses the machinery we've developed so far. Then we're going to basically give a collection of, I don't know if I should call them lemmas or corollaries, basically easy results that we're going to just scoop up and put in one place as a consequence of this machinery. It sort of feels like we're entitled to some easy stuff once in a while because we've built all this machinery up about abstract nonsense involving filtering categories and now exact functors. Feels like we're entitled to a few easy propositions. So without any further ado, let's get into it. We have first the proposition I promised you just a moment ago, which is that if f is a functor c to d, and f has a right adjoint, then f is right exact. And the proof of this is pretty straightforward. It's actually just a consequence of all of the definitions. So suppose that we have our right adjoint G. I always get confused with this terminology, like has a right adjoint versus is a right adjoint. But so if F has a right adjoint, then F is the left adjoint. So we have this situation for some functor G. And this gives us, because of the adjunction, an isomorphism on Hom sets for any u and v in the respective categories. We have Hom d f of u v. My u and v look very much the same. Let's try to make them different. Is isomorphic to Hom in C u g of v. Like so. And the important thing about this is this isomorphism on Hom sets gives us an equivalence of categories between C lower v and C upper, oops, that's getting ahead of myself, C upper g of v. But the important thing about this equivalence is that this guy has a terminal object. Namely the identity map, or the identity between G of V's. And so this makes it a filtering category. Oops, sorry about that. And this is our definition of exactness, or at least right exactness. So that finishes the proof of this proposition. So that was pretty painless. When I was learning about these notions and trying to get an intuition for this, I was told on Stack Exchange that this notion of exactness has no intuition for it. It's just one of these maximally correct definitions that makes proving theorems really easy. Of course, when I saw that, I was very proud to find an intuition in terms of basic notions that we're familiar with. But also, I agree that the maximal correctness part, that seems very true here, because we sort of get very easy results like this. Okay, let's continue now. I want to show, again with this, I want to show a whole bunch of examples. Kashiwara and Shapira call these a mix of things ranging from like propositions to lemmas or maybe corollaries. I forget what they call them, but they're all very simple and they're basically just examples. So let's just make a list of them. The most important example is the example we all know from commutative algebra, which is that Hom as a functor from C op cross C into set is left exact in both arguments. And this might be a tiny bit confusing because you might be used to thinking of like Hom as having a covariant and contravariant argument, but remember we wrote this as C op cross C, so we've taken that into consideration already. And since I've opted the first argument, now it becomes left exact in both of them. And I'm not going to go bother to go through the proofs of these. I want to make this list and sort of do this quickly. If you want to see a proof of these things, Kashiwara and Shapira contain a bunch of them, but also none of them are very difficult. So you can, if you can't do it for some reason, you could ask in the comments and I'll probably write up a proof, or you could ask in the Discord. The Discord is sort of quiet. So feel free, if you're confused, to generate some activity by asking a question. Okay, next, suppose that C is a category. I didn't say this, but I'm going to assume C has every limit that I need to make whatever I say true. So sometimes if I'm talking about limits of a particular shape, I'm talking about, taking, in this next one, I'm going to say that C is a category, darn words, how do I say this? What I want to say is that the functor lim, which eats functors out of an indexing category into a given category, therefore diagrams, and evaluates them, I want to say that that's left exact. This only makes sense, though, if C actually has limits of those shapes. So, through all of these things, I don't want to worry about this. I don't want to keep saying the same thing over and over and over again. So whenever I'm talking about limits of any type, I'm going to assume that C actually has those limits. Okay, so now we can continue. This one's very easy, which is just a small product of left exacts is left exact. Okay, 4. If I is filtrant, then lim to set, and also into R modules are exact. And finally, when I is small, the product functor is exact. Okay. Now, like I said, I want to spend the rest of this video, hopefully not too long, cleaning up some low-hanging propositions, all of which should be very easy for us to prove now. At least I hope so. We'll see if I get stuck somewhere. But let's just see if we can elaborate a bit. Call this one a lemma. So C, a category with finite projective limits and inductive limits indexed by a category I, and we assume that such limits are exact. Then they are also stable by base change. And this is a very cute proof. So what we do is we consider an inductive system xi. And then I look at morphisms, y to z, and lim xi to z. What I do is I build a sort of stupid inductive system out of this. Yi and zi. But whatever these guys are, it doesn't matter as long as it's an inductive system. And every yi equals y, every zi equals z, and all maps are the identity. So this setup enables us to write the following expression meaningfully. We have lim I xi, and now we take the fiber product over the limit of the zi's and the limit of the yi's. And I want to consider this object. Now, this object, which looks a little bit complicated at the moment, is actually easy to recognize. And the reason is because we know that lim I xi fibered over z times y is isomorphic to lim xi fibered over zi yi. And this limit now commutes with everything. And so, well, I guess that's what I have to explain. Since I is connected, these latter two limits do nothing, as we saw in chapter 2. And so I can exchange the limit with the limit of each of these arguments. And then these last two limits do nothing because we know that these limits are boring because, like I said, these guys are connected. And so this is in turn isomorphic to the limit I want, which is the limit over I xi fiber over z with y. And that's what I want to prove. Okay, next, another so-called lemma. Phi j to I is a left exact functor. Then it is cofinal. And in particular, I'll put this maybe down here in parens. In particular, if phi has a left adjoint, phi is cofinal. Just combining what we did previously. And this is completely trivial. And just kidding, I'll say a few words. The reason is a cofiltrant category is connected. And so this follows from the theory of cofinal functors that we saw previously in chapter 2. I think it's chapter 2. Forget exactly which video. I can try to go back and see if I can link it here, if I can find it. Okay, we got a couple more, also very easy. Again, we have phi j to I of some functor. This time I is filtrant, and phi is right exact. Then j is also filtrant. And now, so this guy follows from proposition in chapter 2, which I'll attach. What we do is you just take the two functors to be the same. At least, pretty sure that's what you're supposed to do. So we'll attach that. Actually, there's a limit to how many things I can attach, so I'm not sure if I'll be able to attach the previous card, if I can attach this one also. But I'll try. I'll do my best. I'm new to this YouTube stuff. All right, and our last guy should also be very simple. And here we have F, C to D, G, D to E. Two functors, both right exact. Then G compose F is right exact as well. And of course, in commutative algebra, this is very easy because if your definition is preserves exact sequences, then they both preserve exact sequences, so you're done. But here we have to give a slightly different proof because we don't have exactly that notion, but we have this generalized notion. So what do? Since G is right exact, what this means is that the category DZ is filtrant for any Z in E. But now, CZ to DZ, the induced functor, is again right exact. Since for any Y, DZ sub Y is equivalent to CY, which is filtrant, since F is right exact. Now we just use the previous proposition. Okay, and I think that's going to be it for today. Next time, I think we're picking up with... There's more in this section. This is a very dense section. I think the next topic is on something called small functors. I forget exactly, but that we're going to be picking up there with our next notion. Okay, guys, hopefully you are continuing to enjoy this, and I'll catch you guys next time. Take care.